Here is the key for quiz number 8. The first question asks us about this molecule, and basically it's telling us this is the product of a Diels-Alder. How do we make it? So we could think about it from this perspective. What molecules would we combine to produce this Diels-Alder product? And so we can remember that those two bonds are probably created during this reaction. And so here is the diene, which will make the left half of the molecule. And then here is the dienophile, and it's going to have another carboxylic acid attached to it. But if we observe the stereochemical relationship between the acids in the product, they are trans. And so they should be trans in the starting material as well, which means we should draw them like this. And so we react these two compounds together, we should be able to make the given product right there. For question 2, we're asked to predict the major product of this Diels-Alder reaction, and we're given unsymmetrical diene and dienophile. And so it's important to remember that we can have the larger delta positive at the bottom carbon on the dienophile. And if we were to draw some resonance, we could put a negative charge on that carbon, so we'd have a delta minus on that carbon in the starting material. So let's line them up so the delta minus and the delta positive line up with each other. And now we can draw our Diels-Alder arrows. That's the wrong. And the product would then have, again, a 6-membered ring, the alkene in the back. And we'd have our ketone substituent there, and we would be able to make both versions of this enantiomer, or this chiral molecule, so we should indicate plus minus as the mixture of products. But this would be how we would identify the regiochemistry, or the substitution pattern of our product. Question 3 asks about all possible products for the addition of HCl to this molecule. And so we can basically put a chlorine on any of these carbons bearing the alkene, and we could also have a 1,4 addition. So we should be able to draw several options here. And I think I drew a bit too much right here. So we could have 1,2 additions with all of these, and then we could get a 1,4 addition where the alkene moves. And we could get those two. So this is all well and good, but probably a better way to ask this question would be to show me the kinetic and show me the thermodynamic product. And we know that the kinetic product will form fastest, and it's going to be the 1,2 addition typically. And if we draw a mechanism, we can explore the different potential stabilized cations. That is one of them, of course. And the other one, I'll use green in this case, would come from the other alkene. This is one of those cations, and then this one would be the resonance stabilized. The resonance version, the second resonance structure. Now we could evaluate these two cations in terms of their stability. Secondary for the blue one. Secondary, tertiary for the green one. So most likely the green one will form first, regardless of our thermodynamic versus kinetic product. This is where we then can branch out into forming the thermodynamic or the kinetic. So in order to make the kinetic product, we would avoid the rearrangement or the movement of the resonance and just add our chlorine there. In order to form the thermodynamic product, we would use the resonance to form the 1,4 addition. Here is the key for quiz 9 and 10. The first question has quite a bit of information on the first page, and then the second page has the data. We'll look at that in a second. First off, we want to look at the M plus peak. This is in the mass spectrum, and that tells us that our compound weighs 100 grams per mole. The M plus 1 plus peak tells us that there are 6 carbons in our molecule. The M over Z equals 57 peak essentially tells us that we lost some number to get 57 remaining mass units. So we've lost 43 grams per mole. And that means the fragment that we lost weighs 43. Typically a 43 mass number fragment is C3H7. 3 times 12 equals 36, plus 7 hydrogens equals 43. So the fragment we lost is either a propyl group or an isopropyl group. We don't know which one yet. We don't have enough information to decipher that. But we do know that our structure should have either a 3-carbon group like this that could be easily lost, or an isopropyl group like that could be easily lost. Let's go to the next page and look at the IR spectrum. So here is the data from the first question. Let's first investigate the IR spectrum, and that is right here. Remember that our formula is C6H something, and we're going to have 100 grams per mole. So the IR spectrum seems to imply there's an OH group right here. So I'm going to put an OH here just so I remember that. Other things that are interesting, this peak right here is just above 3,000, so that is most likely some sort of hydrogen on an alkene. So we have CH of the SP2 variety, and then this peak here that's near 1650 or so, it's about medium to low absorbance or medium to weak absorbance. That is most likely a double bond, a CC double bond. And I expect to see that because I already observed that we have this peak right here that indicates that I have some sort of hydrogen attached to an sp2 carbon. And that's really all the information I want to get from this IR spectrum. And already it gave me a lot of information, right? I have some more information about the formula. I know there's an O, at least one O in it. And I know that there's a double bond of some sort in this formula, a CC double bond. Let's look at the carbon spectrum that's here in a vertical orientation. This is not a peak, this is just the edge of the spectrum. Same thing with this at a little less than 0. And so we want to count the peaks that are in between these two lines, and there are 1, 2, 3, 4, 5, 6. So there are 6 separate, or 6 different carbons. That's the word I'm looking for. 6 different carbons in my molecule, and because my mass spectrum already told me I had 6 carbons, I know I have all 6 carbons accounted for, and they're all different, so there's no symmetry in this molecule. And I can also look at a couple of interesting carbons here. Between 50 and 100 are carbons that typically would be attached to electronegative groups. I know I have an O here, so most likely this carbon is attached to that O. And between 100 and 150 are carbons that are parts of alkenes or aromatic rings. I think I don't have an aromatic ring because that would require all 6 carbons, and I would have to have a totally unsymmetrical aromatic ring, but I don't think I have enough other substituents to make this ring unsymmetrical. So I think these are just part of the CC double bond that I observed on the IR spectrum. So I haven't really got a lot more information from the carbon. I know that this is a CO, and I know that these two are probably part of the CC double bond. And then if you read the instructions at the beginning of this quiz, it said to ignore the proton NMR spectrum. It's just there for your information. We don't need it to solve for the spectrum, for the structure. But I think since we have it here, we might as well take a look at it. The first thing I think is to turn these numbers into whole number integers. And to do that, we typically divide by the smallest of the numbers here. These are just random integrations that the computer might spit out. And so I'm going to divide by about 12.3 or 12 and a half. So I'm going to turn that one into 1H. This one's close enough to 12 and a half. I'm going to turn that into 1H. 1H up on top as well. 26.2, pretty darn close to twice my number. 37, pretty darn close to 3 times my number. And 50 is pretty darn close to 4 times my number. And so let's see if these add up to any sort of number that might help us. 3 and 4 is 7, 8, 9, 10, 11, 12. So what if my formula is C6H12O1? Does that add up to 100? 6 times 12 is 72, plus 12, plus 16, and I believe that does add up to 100. So this is a perfectly reasonable formula. I can't have any more oxygens because that would require losing one of my carbons. I know I have exactly 6 carbons. And I know I have at least 1 O, and that really only leaves 12 more units to have hydrogens, and that seems to correspond with what my NMR spectrum is showing us. So I see one methyl group here. It's got a really weird looking splitting pattern. I'm not going to try to decipher that. I've got a 4 hydrogen signal here. This is most likely 2 CH2s, of course, because if I had a CH4, that is methane, and I would have a separate molecule in that case, and that's not going to be very logical. This is a single peak for 1H. That might be the OH. This one might be the OH. And out here, in the 5 to 6 to 6.5 region, these are probably the alkenes. And you can see here that I have 2 hydrogens on one part of the alkene, 1 hydrogen on the other. So most likely my alkene is on the end of the molecule. So let's go back to the page with questions and answer the rest of them. What information does the IR spectrum give you at 3350? That was the very broad hump, the OH stretch. The medium absorption at 3080, that again was the, actually it's the CH stretch here, so let's be a little more specific. That is showing the stretch of the CH bond on an alkene. And in the medium absorption at 1645, that is that's a CC double bond. It cannot be a carbonyl because I've already accounted for the only O that's present in my formula, the O and the OH. All right, so we already came up with a formula. We did observe the peak at 3350, so the formula is C6H12O, and we knew that because we knew that the mass was 100 grams per mole. Then we're asked to calculate the HDI. 6 carbons times 2 plus 2 minus 12 hydrogens. Oxygens don't count, divided by 2. This equals 12 plus 2 is 14, minus 12 is 2, 2 over 2 is 1. I have 1 HDI, so 1 ring or pi bond. What are the peaks at 141 and 114 ppm in the carbon-13 spectrum tell me? That tells me I have a CC double bond. What does the peak at 73 tell me? That tells me that I have a carbon attached to an OH, or at least an electronegative element. There is only one of those in this formula, so it has to be the O. How many chemically unique carbons are present in the molecule? 6. We know that from counting on the carbon-13 NMR spectrum. Okay, so let's propose a structure. What parts do I have? I have an OH. I have what I suspect is an alkene on the end of a molecule. And if you remember from my discussion of the mass spectrum, I have this 3-carbon fragment. We can exclude this 3-carbon fragment because this has 2 equivalent carbons. Those are the CH3s. So I know that I have no symmetry in this molecule, so I cannot have this isopropyl group. And that leaves, what did I leave out here? I have, let's count carbons. 1, 2, 3, 4, 5. I have 1 more carbon that I need to deal with. And how many hydrogens did I leave out? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 1 hydrogen, and it's probably attached to this carbon. So I need to put these pieces together. There are, of course, 3 other attachment points on this carbon. There's only 1 attachment point on the OH. There's only one attachment point on the alkene. There's only one attachment point on this propyl group, so they all need to be attached to this carbon. So there's my carbon with the H, there's the OH, and there's the propyl group. And so I can draw this a little more clearly if I don't include the C. This would be the best structure for all of this data. It fits the formula, it fits the mass, and it fits the chemically unique number of carbons. Here is question 2. We're asked to predict the major products or reactants for the following reactions. So this setup here is hopefully obvious that it is a Diels-Alder reaction. We're going to get a bicyclic structure because we start with a cyclic diene. So this carbon here will be the bridgehead carbon, so we need to draw that structure. We need to add the alkene that's formed in the back of that carbon. So if we want to keep track of this carbon, sometimes it's helpful to put markers on our drawing. And then we'll also have another ring from the starting material of the dienophile. So we're actually making a new ring, and we're retaining 2 other rings. So we should have 3 rings in our structure. And I need to try to draw this in a 6-membered ring. That's going to be a little bit of a challenge, but let's see, 1, 2, 3, 4, 5, 6. And then I'd have, so the ring's a bit misshapen, but it would be the endo product we know is more favorable. So this 6-membered ring is pointed down below this 6-membered new ring that we've formed. It's pointed away from the bridgehead carbon. That's what we mean by endo. And because this diene is symmetrical, there's no reason to draw it with the alkene over here. That would be just the enantiomer here. So we can write plus minus and leave it at that. That would be the product for number 1. The second ring reacts a epoxide with an alcohol and some acid, and we know that we're going to ring open the protonated epoxide at the more substituted side, and after removing the extra hydrogen, we end up with that substitution pattern. Let's look at this one at the box now. We're asked to basically install an ethyl group onto this alcohol. So we need to deprotonate the alcohol first. Typically we use Na sodium hydride. Let me get rid of this. Sodium hydride. The second step is ethyl chloride as the electrophile. So the first step basically makes that alkoxide, and we can do an SN2 to put the ethyl on. The last question here is taking this alcohol and reacting with sodium hydride, then an epoxide, following up with water. So we already just did this reaction. We're going to make the alkoxide. That'll be step 1. Step 2, ring opens the epoxide at the less substituted position. And step 3 protonates the O- that's created from the ring opening of the epoxide. So that would be the desired product in this case. Lastly, we're asked to provide IUPAC names for these molecules. It's probably better to name this molecule as a substituted pentane. So we would have 1,2-epoxy pentane as the sort of the base of our molecule, giving us a 4-chloro. And we do have stereochemistry at 2 positions here. Let's go ahead and analyze that. I'm going to look at the stereochemistry at carbon 2. The oxygen is priority 1. The carbon bearing the O is priority 2. And the rest of the molecule is priority 3. And so if I count 1, 2, 3, the hydrogen is in the back, so 2 is R. Let me change colors and analyze the carbon bearing the chlorine. The chlorine is number 1. The rest of the molecule is number 2, and the methyl is number 3. If I count 1, 2, 3, that again gives me clockwise, but the hydrogen is pointing towards us, so this should be S. Let's go ahead and put our name together now. We have 4S. This should be 2R4S. This would be 4-chloro 1,2-epoxy pentane. And the other, you could also name this as a substituted oxirane, which would have a substituent at carbon number 1 here. We'd have a different numbering scheme here. Actually, that would be carbon. If we named it as a substituted oxirane, which I don't recommend, we would have this numbering scheme, the black numbers. So we would still have a substituent at carbon 2, except that would be a complex substituent because it would have a chlorine on a stereocenter as part of the substituent. So just be a little more complex to name. I would prefer to go with this one. It's just easier to understand, I think. Okay, let's look at this ring. This is a cyclopropyl ring. And we have an ether functional group. Sorry, this is cyclopentyl. I'll fix that. And then we have a propyl group on the other side. So you could name this as cyclopentyl propyl ether, if you wanted to. You could also name it as propoxide cyclopentane. I think we have to modify that a little bit. Propoxy cyclopentane. Yes, so either of these options would be a proper name. This does look like a stereocenter at first glance, but of course this ring is symmetrical, so there are two equivalent sides to the ring. This is not a stereocenter, so don't try to identify that as R or S. All we need to do is label the two pieces of our ether, cyclopentyl propyl ether if we want to, or we could name this piece as a substituent on our cyclopentane ring. So we could call it propoxy cyclopentane. I didn't put a 1 here because there's only one substituent. It's going to be at the 1 carbon. I don't need to list that off. All right, question number 6. We're supposed to propose a reasonable synthesis of both of these molecules. In this case, of course, the first case, I need to make that carbon-carbon bond somehow and then end up with a bromine right here. So I can certainly make that carbon-carbon bond through a number of ways of turning benzene into a nucleophile. One clue is that this is the only enantiomer formed. So if I want to put that, if I want to make this bond while preserving my ability to make only this enantiomer, not to make a racemic mixture, I also need to observe that I'm adding these pieces to my benzene. It may not have a bromine on it. It might have another functional group there that I can easily convert to a bromine, but I'm adding, let's see, it looks like a 4-carbon chain or a 5-carbon chain with a functional group on the second carbon. This is a good hint that I need to use an epoxide. I can ring open an epoxide with a strong nucleophile and obtain a OH group on the second carbon of what used to be the epoxide. I know how to turn an OH group into a Br. So let's draw my target molecule. I think PBr3 will turn my OH into a Br. So I think that is my new target. That plus PBr3 will give me the product. If I make only this enantiomer, again, making this bond, I can do that through the appropriately shaped epoxide. That's supposed to be a dash there. So that stereocenter is fixed when I buy this epoxide. I buy just the one enantiomer. I ring open it using phenyl Grignard. First step is the epoxide, second step, mild acid workup. And I obtain only this enantiomer because I purchased only that enantiomer of epoxide. I can do that just by buying it from the chemical company. And then, of course, making the phenyl Grignard, that's just first step Mg, first step Br2, Fe, Br3, second step Mg, starting with benzene. So that would be, let's see, first step is to add the bromine, second step is the Grignard, that's 2, third step mixing it with the epoxide is 3, and then turning the OH into a bromine is 4. So it's a little 4-step synthesis of this molecule. Let's look at the second option here. We start with cyclohexanol and we make a methyl cyclohexene oxide, or a cyclohexene epoxide. I can make the epoxide plus the enantiomer, so I'm going to make both versions of this epoxide from the alkene in this position. So let's do that as my final step. That seems very reasonable to make the final functional group. So now the question becomes, how do I take this alcohol and turn it into this alkene? And of course I need to add a methyl group here and then have an ability to make an alkene. So how can I add a methyl group to an alcohol? I don't think I can. I can add a methyl group as a Grignard, and I can add it to an epoxide or a carbonyl species, but I can't add it to an alcohol. But I have easy access to a carbonyl species right here. And I can just oxidize that alcohol to the ketone. Then I can add methyl Grignard, and I think this is going to be pretty easy to turn into the alkene. I can actually just do H2SO4 in an E1 dehydration. That should work. Or I could tosylate the OH and then use a strong base like ethoxide to affect that elimination. This is the most substituted alkene, so it should be easy to make. Nature wants to make this anyways, so it should be pretty easy for us to make. So we start this off oxidizing the alcohol to the ketone, then we add a carbon, a methyl Grignard, to get to a tertiary alcohol. We can eliminate to make an alkene, and then we can turn that alkene into an epoxide with MCPBA. On to question number 5. We're asked to propose a reasonable product for both reactions and then also a arrow pushing mechanism. So since we use the arrow pushing mechanism to solve for the product, we might as well just start with that. This is strong nucleophilic conditions or basic conditions. So we're going to open the epoxide using our Grignard nucleophile from the less substituted side. So there's my new ethyl group, and then of course work up with water or mild acid, either one will work, gives us the protonated alcohol, or the product, the alcohol product. The second reaction involves a thiol with strong base. We can deprotonate the thiol with the strong base to make a better nucleophile. And then we can use the thiolate anion in an SN2 reaction to substitute that bromine. And in this case, let's see, we're going to have that stereocenter. We do have inversion of stereochemistry, so let's just make sure I've done that. 1, 2, let's use a different color here. 1, 2, 3. That is R. And then 1, 2, 3. Sorry, this is not R. This is S because my bromine is in the back position. The hydrogen's facing towards us. And now I have 1, 2, 3 clockwise again. This is now R. So I have inverted this stereocenter with my arrow push and in my drawing. So this is the proper product for this reaction 5B.